We're now in section 3.4, which is entitled Library of Functions and Piecewise Defined Functions. The library of functions can be thought of more of as families, and once we know the general shape of the families, then it's pretty simple to go from there. And so realize that there are several different families of functions that we can look at, and so that's what I will be doing here right at first. First of all, we have the constant function. The constant function is basically going to look like that. It's a horizontal line. It's nothing major, it's nothing fun, but this would be the constant function. It is a function. It will say something like y equals 2 or something similar to that. Then we get the identity function. The identity function goes like this. And it will be y equals x. Or, yeah, y equals x. Plain and simple. Then we get the square function. Square function are the parabolas that you are all accustomed to. And so we get something that looks like this. This is a square function, which basically means we will have x squared in the equation. And we can do cube functions, which looks roughly like this. These are the cube functions. And very important to realize that cube functions may be inverted as well as the square functions, as well as the identity functions. They may be opposite of what they are shown here. Continuing with more families, we get the square root function. Square root function looks a lot like that. Notice it stops right here at 0. So this is the square root function. Cubed root function does not stop. Looks something like that. This is the cube root function. Continuing, we get a reciprocal function. Which looks like that. And then we get a very common one that we are very well aware of. The absolute value function. And then finally, we have one that chances are you have probably not seen, or if you have seen it, you haven't seen a whole lot of it. And that is the greatest integer function. The greatest integer function looks like this. It's called a step function, and hopefully it's pretty obvious as to why it's called that. Basically, anytime you see this, it will look very similar to that. Now, there are many different symbols, but in this particular book and in this class, it will be shown with INT, the letters I-N-T, and then integer of x. That's what this will most look like. By the way, working our way back up, square will be x squared, cube right here would be x to the third power. Square root would be square root of x. Cube root would be cube root of x. Reciprocal, 1 over x. Absolute value of x. And greatest integer will look like that. So now we are actually ready to begin our examples. Example 1 and 2 simply ask us to look at the graph and tell us what particular function is this. Number 1 looks like this and it goes up like that. The only one that looks like that would be the square root function, or option number D for the square root function. Number 2 looks like this, and there's only one function that looks anywhere like that, and that is the reciprocal function, or option number B. Now, how we deal with 3 through 6 is to actually just graph it. We do need to be a little bit more precise than just drawing some numbers. So I'm going to be pointing out on some of the values that need to be had. For example, 3 is f of x equals x cubed. There are 5 points you want to include. 0, 0, 1, 1, 2, 8, negative 1, negative 1, and negative 2, negative 8. Those are the 5 points you absolutely want to have at least the beginning. Now we're going to learn with transformations that we do different things with these. But right off the bat, we want negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. Now with that in mind, let's come back up here and see which values we definitely want along here. Here I want negative 1, negative 1, 0, 0, and 1, 1. Squares would be negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. Cube, I've already said, negative 2, negative 8, negative 1, negative 1, 0, 0, 1, 1, and 2, 8. Square root, there are 3 of them. 0, 0, 1, 1, and 4, 2. If you have room, 9, 3 would be the next logical one to have. Cubed root. Cubed root, the values I want you to have would be negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Reciprocal. Now these are not so nice, so let's come back to these a little bit later. The points I need here would be negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. Greatest integer, you're just going to have the steps, and once you get used to them, your steps will look like this. So there's no particular values, although realize 0, 0 is filled in. This point right here would just be the point 1, 0, but it's open here, but right at 1, 1, it's filled in, goes across until 2, then this is until 3, until 4, and until 5. Now reciprocal, these are the values I really need you to put in. Negative 2, negative 1/2, negative 1, negative 1, and negative 1/2, negative 2. That's 3 of them. The other 3 that you need to do will be on the positive side. 1/2, 2, 1, 1, and 2, 1/2. Those are the 6 points that you need to start out with. Like I said, eventually we're going to be doing what are called transformations. You need to start out with these and then mess with them from that point forward. These are very useful numbers for you to learn all the way through on this first page. Now with that all in mind, we're ready to do number 4. Number 4 is the cubed root of x. I've already given you the 5 important points for that. -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. And then draw it into that smooth curve so that it looks like the cubed root function. Now number 5 is a piecewise function, which means for certain parts of the graph there are different graphs depending on what the particular x values are. And in this case, number 5, we are told let's do -x plus 2 if x is less than 0, and then square root of x plus 3 if x is greater than or equal to 0. Well, the first thing we look at is the -x plus 2, and that's what's going to happen over here on this side of the graph, all the way up until here. -x plus 2. Well, this is the identity, or the inverse identity. Basically, it's -x, so it would be coming down like this if it were just -x. If it said -x, we'd be able to bring it down all the way to here. But we have that -x plus 2. What that means is all of our points are going to be moved up 2 spaces. So it would have been coming down like this and hitting 0, 0. Instead, what it's going to do is it's going to come up here and hit 2. But then it's going to go up at that same rate. So it's going to go like that. Now the problem is, as soon as it has to be less than 0. So it can go all the way up to 0 but not including it. So we need to have a big open circle right at that point so that we know it goes all the way up to 0, but it does not include 0. Then we look at the square root plus 3, square root of x plus 3. Well, the square root would come over here with those points, 0, 0, 1, 1, and 4, 2. Well, but the plus 3 there says move everything up 3. So instead of 0, 0, it's going to go up 3, so that's going to be my first point. Then it was 1, 1. Well, move it up 3 places, 1, 2, 3, so that's going to go right there. And 4, 2 would be here, move it up 3 places, and that's over here. So it's going to go like the square root curve. And that wasn't very good. I'm having a little difficulty today. So we get that and realize that since the piecewise function does say if x is greater than or equal to 0, then we fill it in, since it's got the equal to part. So we fill that part in, and so this is what our piecewise function looks like. It is a broken graph because different parts, it stops one place and then starts somewhere else. And that's really nothing bad. It just happens quite often when we have a piecewise function.